Hello. In this video we're going to take a look at the three-dimensional infinite potential well, also known as the cubic box or cuboidal box if you allow the dimensions to vary. So the potential looks like this. That is, the potential is now a function of a three-dimensional vector x, y and z, and it's 0 if all three of these conditions are met. X is between 0 and L, y is between 0 and L, and z is between 0 and L. And this is for the cubical box. Cuboidal, we'd allow these to take different values, different L's. And it's infinity otherwise. So the time-independent Schrodinger equation takes the following form. The Hamiltonian acting on phi of x, where again this is a three-dimensional vector, is given by minus h bar squared over 2m grad squared phi of x, which equals the energy times phi of x. And grad squared here can be expanded as follows. As is, it's the sum of three terms, the partial derivative of phi with respect to x twice, so d squared phi by dx squared, while holding y, z and t constant, and then the equivalents for y and for z. So this equation is separable. We've already separated the time part in the usual manner, but we can also separate the x, y and z parts. So let's just move this up to the top and do that on the next board. That is, we can separate the three terms. We can label them hx acting on phi, where this is a differential operator defined by this equation, hy of phi, and hz acting on phi. So separating the Hamiltonian into three parts. And then we can separate the energy also into three parts, which will define ex, ey, and ez, where these are just labels. They're not raising to a power or anything like that. So we can always do this, of course. If we have some constant energy, we can just split that constant term into three other parts and ensure that the three add up to the original value. So in doing this, it makes it clear that we're going to have a separable equation. We can do it explicitly with the following substitution. Phi of x, vector x, is equal to function capital X of x, capital Y of y, capital Z of z. If we substitute that in, we get the following result, where in each case we've pulled through the two terms, so y and z, which aren't acted on by the relevant part of the Hamiltonian. So h of x is a differential operator which acts only on x, and the capital X is the only function of x, and so on. We can divide through by x, y, z to get the following result, where each of the terms now is a function of only one of the variables. And on the right-hand side, we can use our expression that we defined before. So the d squared by dx squared is now a total derivative because x is only a function of x. So this is now an ordinary differential equation. And we know that the solutions take the following form. That is the function x of x. Let's label it with an integer, little n subscript x. Again, x is just a label here. So nx is one of our three integers, and it's equal to this properly normalized wave function, again here nx, pi x over L, and the corresponding eigenenergy is Ex, given the same label, n subscript x, and it takes the form of the 1D result. So putting everything together, we get the same equations for y and z, and this is our total result. So here's our original equation. The solutions are phi of x, multiplying the three separate solutions back together, labelled by a vector of integers n, where n is defined by nx, ny, nz, the solutions to the three independent equations. Each of these is just a different integer, potentially different. Here's the product of the solutions in the different directions, and the energy, also labelled by vector n, it takes the usual form. So we can define, if we think back to our quantum numbers, remember that's some quantity corresponding to an expectation value which doesn't vary with time. If we look at our three separate Hamiltonians that we separated the original Hamiltonian into, we have this sum of three terms where any two of these terms commute because each one is only a function of one of the different variables. And so what this tells us is that we can define the quantum numbers for each of these different parts of the Hamiltonian. We can define these three quantum numbers at the same time. So we can write states that are labelled by all three of these, and there's no problem with specifying them. We can have simultaneous knowledge of nx, ny, and nz. So in ket notation, it's convenient to define the following. That is our wave function phi n of x is the x projection, where x is now the vector, but it's still projection into a three-dimensional position space now, of some ket nx, ny, nz, where we have the following time-independent Schrodinger equation with En defined above. So the ground state of the system, for example, let's clear the board. The ground state of the system is the state labeled with a ket labeled by 1, 1, 1. So all of the n's are as low as possible, and the corresponding energy eigenvalue is E 1, 1, 1. We substitute the ones in and we find h bar squared pi squared over 2m L squared multiplied by 3. And the ground state is unique. There's only one state with that energy. However, the first excited state, there are three independent states which all have the same energy. So these are the states with the next lowest energy, and all three of these have the same energy, which is stated here. So now we start to have degenerate states, multiple different states with the same energies. So some of the results we've seen before relied on having non-degenerate eigenvalues. Some of those will disappear, but in fact, it's still possible to find an orthonormal basis for these states in the following form. So for our vector, for our state nx, ny, and z, if we take another state mx, my, mz with these different integers or potentially the same, we find that the inner product of these two states is a product of the Kronecker deltas for each of the three pairs. So mx has to equal nx, otherwise this is 0 and the whole thing is 0. So we need mx equals nx, my equals ny, mz equals nz. This is quite straightforward to prove, as usual, by insertion of the identity, which takes the following form. That is, we've just taken this inner product here and inserted a complete set of position states, where again these are three-dimensional now, and so our volume integral must be dx, dy, dz. But we know what this is from the previous board. It's just the wave function we found before, and therefore this must be its complex conjugate. That is, these two things read. So sine mx pi x over L, same for y and z, and then the same for the n's. But we can just separate these into three separate integrals, each of which multiplies the others. So the first is just 2 over L, integral over 0 to L of dx, of the sine of mx pi x over L, sine nx pi x over L. And you get the same with x changed to y and then x changed to z. But this is nothing other than the integral we used in the one-dimensional infinite potential well, which equals our Kronecker delta. So this is nothing other than the Kronecker delta, telling us that mx has to equal nx. You get the same for the y and z terms, and so this is how you prove this result up here. So in this case, actually, we have degenerate states, which is potentially a problem, but actually it's possible to choose an orthonormal basis, just like we did in the 1D case. It's not really much more difficult. Okay, thank you for your time.